This is an example of using polar coordinates. Let's read the problem statement. A robotic arm extends along a path equal to r equals 1 plus 0.5 cosine theta meters. At theta equals pi over 4 radians and theta dot equals 0.5 radians per second and theta double dot equals 0.7 radians per second squared, find the velocity and acceleration of point A. All right, so we have this robotic arm, and at the end, there's a particle. And we know how the arm's moving. The problem statement tells us that. So from that information, we can find the velocity and acceleration of point A. Now, I've already told you that we're going to use polar coordinates. But if you were just reading this problem, you would have to decide which coordinate system to use. We have the xy, the nt, and the polar coordinates. So which one should you use? Well, this problem is fairly obvious. What information we're given is r, theta, theta dot, and theta double dot. That pretty strongly points you to using the r theta or polar coordinates. So once you decide which coordinate system that you want to use, you usually write down the formulas that can help you solve the problem. In this case, the polar coordinate has a velocity and acceleration equation as a function of these known variables. So let's write that down and see what we have and what we need. If you look at the velocity equation, we have r dot. We need to find that because the problem statement doesn't give that to us explicitly. However, it gives us an r function. So we would have no problem taking the time derivative of that. The next term has r and theta dot. We know those, so we can just plug in the numbers. The acceleration equation, we need to find r double dot, and the rest we will know. All right, so let's get started with the velocity. So here's the velocity equation. We already discussed that we need to find r dot, and we know r and theta dot. So r is given in the problem statement. All we need to do is plug in theta equals pi over 4, which is the position that we need the velocity and acceleration for. So we get 1.354 meters. Next, we can take the r equation and take the time derivative of it. So if you're a little rusty on your derivatives, please look at Appendix B to kind of dust off the cobwebs. But if you look at r, and if we want to take the time derivative of r, well, 1 is just a constant, so that goes away. The time derivative of 1 is 0. The next one is 0.5 cosine theta. We're going to use the chain rule for that. So when we take the derivative of a function, and inside the function there's a variable that is dependent on time, we need to use the chain rule. So we're going to take the derivative of the outside and multiply it by the derivative of the inside. So the derivative of the outside, which is cosine theta, would be minus sine theta. The derivative of the inside, so the derivative of theta, is theta dot. So we get minus 0.5 theta dot sine theta. We plug in theta equals pi over 4, and we get minus 0.177 meters per second. All right, we have all the information we need to find a numerical value for the velocity. So we just plug those in and come up with our final velocity in the r and theta direction at theta equals pi over 4. All right, so let's go to the acceleration. The acceleration, we have everything except for r double dot. So let's look at taking the time derivative of r dot. So taking the time derivative of r dot, we're going to use both the product rule and the chain rule because we have theta dot times sine theta, so we'll need the product rule for that. And we have sine theta, which we use the chain rule for that. All right, so I'm just going to pull out the 0.5, the minus 0.5 as a constant, and take the derivative of everything else. So the product rule is the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first is theta double dot times the second, which is sine theta. Derivative of the second would be cosine theta, theta dot. And then we're going to multiply another theta dot. So we have theta dot squared cosine theta. We plug in theta equals pi over 4, and we get 0.336 meters per second squared. Now we have all the information we need to come up with a numerical value for the acceleration. So we just plug in and get the r direction and theta direction components of the acceleration. And that completes the problem.